All right, thank you so much. Welcome, everyone. Thank you for coming. Good afternoon. So my name is Saurabh. I'm part of the OpenSearch group at AWS. I lead the core search, engineering performance, and infrastructure team. I know I'm in between you and your next coffee break, so I'll try to make sure that it's all worth it. So today we'll be diving into how the search is evolving and how OpenSearch is, taking a leap ahead to meet these modern demands of the new search generations. A quick view on the agenda. So we'll start with a little bit of history on the search, like how the typical lexical search used to be the primary thing. Now with semantic, hybrid, and moving towards the conversational search with the generative AI, we'll give a brief overview of OpenSearch Foundation, who are we, what do we do, how we have come this far. We'll talk a little bit more on the technical deep dive on new things that have come up in the latest open source version of OpenSearch, which is 3.0. We'll take some of the real-world examples on hybrid, vector, multimodal search, and definitely the RAG, which is the famous and the most popular theme on this track in the session today. We'll talk about some of the architectural advancement as well, where we'll cover the performance, stability, and observability changes, because these are the core, irrespective of whatever we do on the application side. So we'll reserve some time for Q&A as well. Hopefully, we'll see. All right. Getting into the evolution of search. So why do we care about search? Because search is the heart of OpenSearch, and so since its inception, we have been continuously improving in how the search demands have been changing. So we started with, as a typical search engine in the core search area for text searches. Typical way of doing that is using techniques like BM25, which is going to go ahead across your documents, find the keywords, terms, frequency, and things like that, and that's going to give you the rank, and based on that, you'll have a very good mechanism to do exact matches. However, these searches kind of lack in the semantic understanding. They don't know what your intent is. They know, specific keywords. With the modern advancements, in the last few years that has happened in the ML side and natural language processing, I think we got better at it. Like, for example, at least autocorrection or stemming or synonyms. But still, it was still very much lexical. We didn't have the understanding of semantic. However, with the breakthrough of some of the language models, we got to a place where we could convert these text information into embeddings. Now these embeddings are nothing but a way to represent these text information into numeric vectors, and this is what you can ingest and search, so that now you don't need to find exact, but something which is closest in relevance and gives you the ability for semantic. Eventually, with the evolution to semantic, we got the idea of hybrid, because we want the best of both the worlds. So you want something which is closer to, let's say a sneaker versus a shoe problem, versus if you have a very specific requirement as well. So exact matching can come in together. So that's where hybrid search came in. So that kind of allowed us to be more, insightful on the searches. However, with more advancement on the multimodal search requirements, like, for example, the LLM models and the embedding generation, not just happened for the text. It moved forward for images, videos, some of the other patterns. So that's where the multimodal search came in. So you could search essentially anything now. And then with the disruption of the advanced GPT-style models, that's where the conversational search came in, where you can back the search for a very precise data or information using building some RAG framework, basically. So you take those information from the search system, put it into LLM, and then you could have like a very concise and dedicated answer for probably what you're looking for. So we'll go into this journey of how OpenSearch is trying to solve this, but we'll take a little bit of step back and try to brief you about what OpenSearch is. So OpenSearch is a 2.0 Apache licensed open source search and analytics tool. It has been managed, it's been there for like 4 years now. It is managed under OpenSearch project under Linux Foundation. And then overall, in the last 4 years, it has seen tremendous growth in not just the community engagement, but also the roadmap on the technical insights that we have taken. Like starting from a very core search engine, it has evolved itself to be a a solid vector engine, which is out there right now and one of the primary choices. We have ability to store embeddings and information to retrieve them much more faster, along with the search context that you have, so that it kind of enables like one go-to platform for all different kind of searches, what we just looked at. So looking into our foundation journey, so typically we went to foundation last year, which is the Linux Foundation, and we have like 16 foundation members right now. So these are like different unique organizations that support OpenSearch right now, and there are 11 of these distinct organizations are part of the technical steering committee. So there's a governing body, there's a technical steering committee who kind of meet very often, and they decide the charter and the roadmap for OpenSearch. We have had tremendous growth in our contributors, so we have 1,000+ contributors right now, and these are just like GitHub contributions. These are actually builders and developers who are contributing on GitHub. Apart from it, we have 1,500+ forum, plus our Slack users who are more like the community member and excited about the product, and they would want to kind of connect with us. This is a quick peek into the foundational members you have, if any of these logos ring a bell. But overall, in this whole journey that we have had, Lucene has been our core soul, which kind of ensures that OpenSearch, even though it's kind of evolving into all of these different aspects of search, it doesn't compromise on speed and reliability, which is the most important thing for any search engines. All right, so taking a step back and then going back to our search paradigms. So we did touch upon all of these different use cases. Let me give you some live examples for this. For example, semantic search. I kind of took the example of the running shoes for trail. So you could just go ahead on an e-commerce site, and then you can search this, probably give this very natural language sentence or a keywords, and then it's going to give you some results based on maybe a Nike shoe or something like that. However, in hybrid, you can even combine that with a very specific information, like maybe a size 10, black color, or things like that. In multimodal, we all use it in our day-to-day life. Like, for example, you must be using Spotify or Shazam to find an audio pattern and detect a song. You must be using Google Lens to kind of identify matches for an image, or maybe security cameras, which are kind of detecting face recognition or real-time motion. The GPT-style chats are also very common these days. For example, if I'm in Berlin, I would probably look for a day itinerary. I want to go around, maybe have a beer somewhere, so I would ask for recommendations. So it's going to pull those very unique information from billions of vectors and then source them into LLM, so that now my query can be answered in a very personalized way. So how is OpenSearch kind of addressing all of this? So with 3.0, which is the last major release, it happened about a month ago, and 3.0 was the major release after nearly 2 years. So it did pack a ton of things, primarily not just from the breaking changes, but also from the performance improvements across just different areas. And we'll kind of go deep into all of these. But I want to give a very top-level overview. From the infrastructure performance, so Lucene 10, I think some of you would have attended the talk today from Adrian this morning, like how Lucene 10 brought in the capabilities for CPU, IO concurrency improvements, and also it kind of brought in new concepts of index, skip lists, and things like that. JDK 21 kind of empower, bringing its own new improvements. So all of that kind of went into OpenSearch 3.0. But not just that, we also targeted some of the query performance improvements, like different range queries, text queries, and different kind of aggregations. So OpenSearch can support tons of aggregations for log analytics use case. So all of them kind of went into OpenSearch 3.0, and the overall goal what we achieved was about 10x throughput and 90% latency reduction compared to the first major version, which was 1.0. And against even the last previous minor version, which was 2.19, we achieved about 24% performance improvement. Also, AI-ML integration became more native in 3.0. So the OpenSearch vector engine kind of brought in the ANN, which was the next, I would say, algorithm or the way of doing your KNN search. So instead of doing the exact search, you would kind of go into and do an approximate KNN search so that you can deal with billions of vectors. We will talk about that scale in more details as we look into the architecture of that. But that kind of enabled us doing the hybrid scoring and enabling all the semantic search workflows. And also, 3.0 brought in some ML connectors, like how do you connect with different open source or maybe proprietary or your local LLMs, so that you could kind of build a RAG framework out of it. Performance and scale, as I talked about, there have been some very targeted performance improvements, which I will cover briefly, like GPU acceleration using some of the NVIDIA algorithms are kind of housed and packed in as part of the OpenSearch 3.0. We introduced a new index altogether, which is a star tree index. It's kind of very promising for log analytics use cases. Like anytime you have like known dimensions, you would kind of use this pre-computed information. And this star tree is a known concept in the database world, which brought it into OpenSearch. So we'll kind of break through into all of these. But let's first start with the OpenSearch vector engine. So this is a very high-level diagram of how OpenSearch vector engine works. So you might have a raw data in form of image, documents, audios. The first step is, of course, extract this, split into chunks, and use some of the ML transformers or models to generate the embeddings. We'll talk more about how this integration works, but the idea is if we can generate this dense vector encodings, what we could do is we could build OpenSearch indexes, which is nothing but different other Lucene indexes distributed among different shards, and then you can go at any scale. And essentially, when you're retrieving this information, you would kind of do either a KNN search or a ANN search based on or you would do a combination of those along with different filtering that you would have for those queries, so that you can retrieve that information and then load it back for the responses. The algorithm. So what is specific about this architecture with 3.0 is specifically that we have build an ability where you can offload these vector embedded index creation to GPU workers using the NVIDIA Kagra algorithm, and then that kind of boost up the whole performance to an extent. So let's go into some of these, right? So I kind of talked about approximate KNN with HNSW. It's kind of very similar to how the KNN works, but ANN is kind of more efficient, especially when there's large scale of vectors and you don't want specific matches, but approximate matches are good for you. So it kind of gives you the ability for about 10x throughput improvement and 90% lower latencies. GPU acceleration, what we saw in the previous, like if you can have a worker fleet where you have GPUs and you could kind of offload your index creation, you would get about 9.3x faster index creation at a cost of which is 3.75 less compared to CPU-only nodes. And this was kind of a benchmarking that we did with like about 10 million vectors that you could create. So even the whole vector creation process reduced from days to just few hours. Disk optimized search. This is something that we all who have been working on the vector side of things understand the limitation that vector runs into with terms of heap and memory. So basically, it's all about how do we reduce the sizes of these vector graphs by either some quantization techniques. So I think OpenSearch did include the binary quantization, which kind of reduced about 2.5x the whole storage size. And then it also kind of introduced some of the compression algorithms to kind of reduce the memory footprint. Derived sources are another interesting aspect. So these are like some of the obvious but not so obvious improvements. Like so if you look at the vector creation, usually when the document is indexed, you would create the vector index, you would create the HNSW, you would kind of also store the actual documents so that you could retrieve them when you have to serve back the request. With derived sources, I think it was pretty impressive and intelligent way of not having to store the actual embeddings or the vectors as part of your source, because you would never need to kind of serve them back to the customer. Anytime you need them or a user is requesting them, you could serve them from the vector index. So there was an indirection that you can probably create. So this kind of helped with 30x reduction in throughput and also 3x reduction in size of your index if you would use derived sources. Now, along with all of this, integrated metadata and filters, which are the core competencies of OpenSearch, because it gives you the rich filtering capabilities. You can even break down this HNSW into a multi-partitioned or multi-tenant graphs, and then apply some filtering so that you don't have to load everything in memory at the same time. There's also some improvement coming up in these areas for like 3.1 probably, where you'd be able to load only partial graphs in memory so that you don't have to load the entire graph, which is typically the requirement today. All right. So now we know how we took, so now we talked about how these embeddings are stored and retrieved. these are the, we want to kind of now touch upon how these embeddings are created using different connectors that OpenSearch can support. So this is a high-level overview. Again, you have different formats of data that's coming in the OpenSearch. Then you have the AI ML connectors, which can create dense vector encoding or sparse vector encoding based on whatever is the requirement. And we named ByteDance because ByteDance was one of the major contributions who helped with the DeepSeek integration. Yeah, but you could use one of these and then, or maybe you could use AWS SageMaker, you can use Hugging Face, or there are a lot of these LLMs that are available that you can kind of integrate and use them to create these embeddings. All right, so now we looked at how to create these embeddings, how to store them, how to retrieve them efficiently. There were further some improvements that happened in the neural and semantic search areas, especially with the introduction of reciprocal rank fusion algorithm. So this is kind of a hybrid optimizer. So a lot of time, the classical hybrid searches works on basically merging the the scores that you have got across different methods, and they will try to kind of find the best position for the document in the final result. So reciprocal rank fusion helps you optimize it by merging based on the occurrence of the rank in which the document is appearing in different methods instead of the absolute score. So that way, it helps you to overrule any specific methods kind of going ahead and creating anomaly in your result set. Why is it important? It's important because it kind of takes away the bootstrap time that you have to invest in kind of tuning your scores and running these tests manually to get to a place where you know what is the right result. It kind of does it for you as part of the heavy lifting. Multimodal and neural sparse search, because inverted index are the core essence of Lucene, and then OpenSearch as well. So with a sparse index, what you can do is basically the embedding which are created, you can create sparse token of it, and then you can store it as part of the inverted indices. So that way your hybrid search can boost up based on the sparse token searches. So you kind of bringing the best of both the worlds, the Lucene index for capability, and also kind of tying this up with the embedded encoding that you can generate and search upon. All right, so now we looked at how these embeddings are created, how they can be stored in an efficient way, disk optimizations, how we can retrieve them efficiently with ANN. So this is a typical setup, or I would say architecture, which was used by one of the partners, Aaron, to kind of create a chatbot application. All the flows that we talked about are being used here. So you have a transformer model. It could be any of those ML connectors that you can use to generate the vector embeddings. Those vector embeddings kind of get into the system, and they are stored at indexes. Once you kind of retrieve them, you use one of the algorithms to retrieve. You use the ranking algorithms to rank them, and then you take those output in documents and source them into LLM. So LLM is so it's now going to personalize this for you based on the query, and it's going to give you a very personalized result. Yep. So this is as simple as that for the RAG framework. All right. So this is just a brief summary on overall GenAI and RAG integrations that we have. So OpenSearch plus LLM is kind of the RAG what we are talking about, because it allows your LLMs not to hallucinate, because the moment you ask them certain questions, you can feed them with a very distinct set of information, and then the whole answers or query can be kind of generated based on that. ML common connectors are the search time inferences and things that we talked about. How do you generate those embeddings? In context search for agent. Yeah, so in 3.0, we did launch an experimental version of model context API as well. So now OpenSearch is positioning itself to become the go-to engine for the agents and related use cases. Real-time updates for LLM is super important, because anytime you want to build these RAG systems, you would want the data to be updated, and OpenSearch is designed to keep this data updated through indexing. So basically, that will help your LLM queries to always remain relevant with the real-time data updates, because your retrieval documents or the focused information is being handled by OpenSearch. So whatever your LLM gets as an input is always the fresh information. Security and privacy. So OpenSearch does give you different level of security, which is like field level security, document level security, multi-tenant segregation. So all of these capabilities, which are core to OpenSearch, is out of the box available whenever you're doing these RAG integrations. Yeah, so this is one of the example which I showed in the initial architecture diagram. So OpenSearch plus DeepSeek with 6.7 billion model, and it was kind of about 10 terabyte of data, and then you could get an answer within less than a second. And for one of the experiments which was done by the community user to showcase this whole thing, and it's available in form of a blog and also videos if you guys want to kind of go ahead and check this out. Okay. So moving ahead of that, I think. So modern search is all not about AI because we do care about efficiency and scalability as much. So with OpenSearch 3.0, we did target some of the very foundational core efficiency and improvements. So I would like to touch upon some of the highlights of it. For example, concurrent segment search. This is something we made it enabled by default in 3.0. So which means that if you have large indexes, which most probably will have large shards, and then which essentially would have large segments, can now achieve concurrency by or more number of segments within the same shard. So all of this can be computed concurrently, giving you a higher throughput that you would have seen otherwise. The concurrent segment search also works with some of the aggregation use cases with the, where you can concurrently do reduce operations. So it kind of helps. So this is one of the foundational things that helped us achieve that 10x improvement against our previous versions. Start reindex for aggregation. So this is typically for log analytics use case, metrics data log, whenever you're trying to query on a known dimension. So you can move some of the heavy lifting to the indexing time, and you can say, oh, if I have users logging from different country, and I want like a per day view of the count. So you could create this mapping in your index, and then what OpenSearch would do is it will pre-create these indexes for you based on the dimension that you would query them, and so that anytime you're going and searching them. So especially this is very effective for high cardinality queries. We have seen reduction of up to 100x in the query time just because of this. And in the size, we haven't seen any a tangible increase just because these dimensions are compressed and they are kind of persisted in form of like just another Lucene index files. So we don't see any regressions on the indexing or I would say sizing. Deeper pagination with point in time was another feature because whenever you paginate and you have a lot of search results, maybe 10,000 of them, a common occurrence with the search system is by the time you kind of navigate, maybe your context is lost or you get timeouts. So with this, the live cursor creation, which was provided by basically OpenSearch, helps you to dissociate from the active index, so that if you have to go to the last page or you go to the 10,000 page, you can actually do that without hitting a timeout. So that was like one of the improvement on the experience side that happened. And then on the range and match queries, which are typically important for both search use cases and log analytics use cases, there were certain techniques that were used in form of early terminations. We used range approximations and things like that. So these are essentially the techniques which were trying to improve on the core algorithms of how do you traverse the BKD tree in the Lucene side, how do you approximate queries, which is a known concept in the database world, so that you don't have to actually go through all the hits, but rather when you have enough information, you could just fail fast and return back the response. So all of this kind of also helped our strategy on sorting. So we saw that improvements in 3.0. Indexing performance was another thing. So it's not all about search. Indexing performance also improved because some of the encoding changes, and we achieved about a 9% improvement in the indexing efficiency. So one of the major highlights that we wanted to call out, which we started in 3.0, is the fundamental way of how OpenSearch communicates, not just back to the client, but also between nodes in order to execute a particular request. So today, OpenSearch it's a distributed system. You could have like 100 of nodes, and then a query which is executing on one node would kind of fan out into data node requests across different nodes that are there, and then there would be execution on all these data nodes. The responses come back to the coordinator node, which is going to do the reduce. And today, this happens in like two phases, where the coordinator node sends the request to all the data nodes. Data nodes is going to do the heavy lifting. They'll create those big arrays of responses. They will send it to the coordinator. Then coordinator will, operate them one by one and try to do the reduce. The challenge with this is, if your data is very high, it's high cardinality or big in size, you would have a lot of memory overhead on both data node and coordinator. And there's not a lot of useful work done on the coordinator while data nodes are doing their job. So we try to introduce a streaming concept where you don't have to do a request response model, but you can open up a bidirectional stream from coordinator to these data nodes. And then what we used was Apache Arrow was one of the it's a very popular project in the Apache side, which kind of gives you the ability to represent data in a columnar format. And in-flight server is a gRPC-based protocol, which is used for communication between data nodes now. So with a combination of this, data nodes and coordinator nodes can now talk in a bidirectional stream, where none of them have to wait by the time the whole query is executing, and then these small batches, the stream of data can flow in, and you don't have to, it saves on memory allocations that you have to create, because Apache Flight by default provides you the ability to write into the neti buffers directly without having to do a deep copy. And then also what it helps with is it gives you the ability to do columnar merges and maybe vectorized computation. So those are the two aspects what we saw. And then data fusion is another layer operator that can come on top of this to kind of achieve joins and have a plan that operates upon, because data fusion it's another Apache project. It's a query engine which can which supports columnar format by default. So this is something that we have started building up. The initial results looks very promising. We have achieved about 2x performance improvement with about half the resource utilization. We are in progress. The experimental work is already there, at least on the transport side of things. So we might be introducing this in some of our aggregations framework very shortly. Okay, so we did touch upon some of the open source improvement that we have had in 3.0. So we will continue to kind of work upon them. Specifically on the streaming side of things, the concurrent segment search is auto-enabled, but we want to expand the scope of it across the board. We have index work going on the indexing side to kind of improve the ability to work with the columnar format and maybe provide you the ways of how you persist them in a more popular Parquet format and things like that, so that Parquet plus Arrow plus data fusion becomes a whole infrastructure in parallel what we have today. So this is just a high-level breakup of the whole performance things we were touching upon. So a good way for us to evaluate the core performance is using the Big Five workload. So Big Five workload is part of the OpenSearch benchmarking, which is a tool. And this is, again, an open source tool that anybody can use to benchmark OpenSearch or similar softwares. We have created a new workload there, which is covering across these 5 different query areas that we mostly care about: text, sorting, terms, range queries, data histogram. And if you look at the timeline and the performance, so you would see like data histogram from 6,000 millisecond has gone down to up to like 100 millisecond. And then similarly, we'll see some of those improvements on the terms, sorting, and all of these buckets. We have had like multiple blogs in past few months, and I would say maybe a year or so, to kind of talk about specifics of how we have achieved these improvements. These are very technical in nature, so if you're interested and you would like to understand more, it's pretty useful. All right, so now we did touch upon some of the performance improvements and core search changes that we did. I would like to also talk about some of the core architectural changes that has happened, which is enabling OpenSearch to become a more cloud-native solution. And the reason is that we have like multiple foundational members, about 14 of them. A lot of them are different enterprises, and they want to use OpenSearch in their ecosystem where they have different applications and microservices, working in conjunction to, through the search platforms they are building. So, which means that we want OpenSearch not to be just a managed system or a system that can be deployed, but it should be more native to the cloud. So some of the things that we have done in the recent past, especially available in 3.0, are the reader-writer separation. This is more about how do you handle the larger workload in a single cluster. So let's say if you have a 1,000-node cluster, and if you would let all nodes do same things, you would not be able to achieve a high isolation or throughput, just because you would not be able to identify very custom resources that you would need for either indexing and search. So reader-writer separation comes at 3.0, as GA in 3.0. It gives you the ability to isolate the node roles, saying that, okay, my X number of nodes are only going to do indexing, my Y number of nodes are going to do only search. You can have different resources for different types of instances. Basically, maybe your indexing needs more memory, so you would have more memory-intensive resources there, versus your query could be needing more CPU, so you could have more CPU-intensive resources there. And it gives you failure isolation. We have seen throughput improvement. We have a recent blog out there. We have seen a more than 2x improvement with a lower cost, because the ability to have dedicated resources kind of helps you in customizing what kind of fleet that you need for your indexing and writing. Protobuf or gRPC-based communication is also introduced. It's experimental right now, but it's again moving towards the requirement that how do enterprises or the existing microservices talk to OpenSearch without having to really build the client into it or follow the request response model. So gRPC it has helped to a good degree on indexing side. Team is, I think there's a lot of work that's going on the search side of query, because we have to in order for it to make work end-to-end, there's a lot of work that needs to happen on the client, on the server side, and also on the security realm, so that you continue to offer the kind of securities, like, for example, document level, field level, and all of that, and that is honored when you move to the new protocol. Pull-based ingestion, this was the work done in partnership with the Uber team. I don't know if they're here. But yeah, this is something that allows the streaming pipelines, like you can have a Kafka stream or you can have a Kinesis. So any of these streams can become a source for ingestion into your open source cluster. And by that, from a push model, your indexing moves to a pull model where your cluster knows, okay, how fast I can go, what is my rate of other things that are happening, maybe background jobs, snapshot queries. So I can adjust that rate based on how fast I can consume. And also, it kind of helps in dynamic sharding, because, dynamic sharding is not there right now, but it opens the gate for that, because tomorrow, if your ingestion load is kind of growing up or you're lagging behind, your system can detect, okay, I have to go faster, so probably I'll spin up more shards on the fly and then try to consume faster from the Kafka these ingestion streams. So last thing I think are some of the top-level observability or application-level improvements. So we did touch upon some of the foundational core, indexing, search, storage. But what is also needed is to have like an interfacing layer which can help you to communicate with OpenSearch, and observability tools and PPL or SQL capabilities come handy as part of that. So 3.0 did launch the PPL query capabilities. It was always there, but it kind of extended with a query planning support. So we're using Apache Calcite, which is another open source Apache project, to have a better understanding of how to plan these queries and execute it in the system. So this kind of gives you the performance boost and also kind of expands the scope of how you can use PPL to interact with OpenSearch. Enhanced query insights and improved monitoring. So this is more part of, if you're an admin of a cluster, or if you're running this cluster, to understand what is your workload, how much resources you're using. So these are like advanced plugins which are available, which will give you a breakdown of top-level end queries which are in the system. You can see, okay, what has been my top hitting queries in the last 1 hour, how much resources they're using, CPU memory. So that way, it just helps you to find the right balance between when you're kind of tuning your workload or identifying how far do you need to go when you're provisioning. Yeah, and then we have the anomalies detector, improvements that has come in as part of our anomaly detection plugin and alerting plugin. So these are like different components which ride on top of the OpenSearch core as different capabilities. So there's, I just wanted to kind of call those out here, which has gone in like 3.0. Yeah. So I would like to kind of, end to, show these are the active community we have. These are the places, at least we have had one or multiple these meetups. So if you are in one of these places, you can physically join these meetups. If you're not, there are meetups online that a lot of community folks join. So please do join us, give your feedback, try OpenSearch, and let us know how we are doing. Thank you. All right.
Thank you very much for that very insightful talk. We do have time for 2 or 3 questions, short questions. I would like to remind you that this is a Q&A and refer all you, or this is not a question, more like a remark to like meeting him on the booth later. Yep. Okay, we'll start with a question from the remote chat. As OpenSearch is forked from Elasticsearch, it inherits some of its characteristics, namely the no separation between the indexing and serving infrastructure. Does OpenSearch have any change for this feature on its roadmap?
So the question is about if it has any indexing and search separation plan on the roadmap.
If you plan on doing something about it.
Correct. So I did cover that in the slide here in the deck. So in 3.0, we did GA for node role separations. Yes, when OpenSearch was forked 4 years ago, there was only 2 node roles, which is data node and coordinator node. So now in 3.0, we have introduced a reader node and a writer node, so where you can have dedicated number of shards for indexing and dedicated number of search node shards. So that way you can scale up your search independent of your scaling, indexing, and then also achieve failure isolation. Yeah.
All right. Any questions from the audience? All right. There's one. And we can have one from the chat afterwards.
Thanks. Hey, thanks for giving the talk. That was really insightful. This is a pretty straightforward one, but is there a release scheduled on AWS for OpenSearch 3?
Yeah, that's true. So if we go to the, our website, must be one of our links here in the QR code. So we have a dedicated release page where we kind of, publish the cadence of the release. So major release usually happens in 1 or 2 years. So I mean, this was the major release after 2 years, but we have minor releases every 8 weeks. So yeah, and the schedule of those releases are pretty much available there.
All right. There's another one from the remote conference. Does OpenSearch support OpenTelemetry to give detailed introspection on query execution performance?
Right. So that's true. So I did touch upon that on the last slide where I was talking about the Query Insights plugin, which kind of gives you the breakup of how your queries are executing within the OpenSearch ecosystem, and then what resources they are utilizing in terms of CPU and memory. So that information is available today, and that is very much important for users and people who are provisioning, so that they can know how to balance and use the cluster.
All right. More questions from the audience? No. All right. Then I'm sure you all have you're waiting for the coffee break. You can meet Saurabh whole conference.
Yes. So I'll be at the OpenSearch booth. Correct. And I have my team with there as well. So please walk in, grab some shirts, and this is your QR code if you want to know more or anything. Yeah. Thank you so much.